So we have our first speaker, Professor Bishakhdatta Gayen from IISc. He's in COS. You already know now him. So today his talk is on role of convection and turbulence in melting of polar ice shelves. So please.
Hi, good morning, everyone. So as I promised yesterday, like now I'm going to cover more about the role of the small scales of the polar melting, and then finally I'll get connection. Okay, all this small scale with the large scale overturning. Okay, so a lot of materials I have to cover, so I might be rushing. Okay, and again, if case I'm missing something, you can always feel free to stop me here or stop me outside the talk. Okay, I can explain more. Okay, so let's start. Okay, why we care about Antarctica? Okay, as you know, the Antarctica holds a huge ice. Okay, which ice we are talking about? This ice is actually rested over the land. Okay, and they extruding over the ocean. So this ice is actually rested over the land. So when this melt, it will going to add water to the ocean. Okay, so that means the ocean volume will going to rise. Of course, it is not the only way you get the sea level rise in the future. There is another way of sea level future. So sea level can rise. Anyone? What is the other way you have a sea level rise in future? Yesterday somebody talked with. Give this hints. Precipitation. But precipitation is coming from the same water and coming up, right? So what is the other way? Sea level rise. Exactly. So thermal expansion, and this is another process is this one. Okay. Of course, Antarctica might be raised because of the ice will gone. Okay, but we are not staying in Antarctica. We're going to stay in northern hemisphere where this water will rise. Okay, we do care about this one. Also, is very important is this water, whatever is coming, is a fresh water. Okay, so fresh water is also very dangerous to our existing overturning circulation pattern. I'll come back to that point. But now we care about this melting of ice, and this ice is actually melting by ice ocean interaction. When you say ice ocean interaction, that means something is happening with the ocean. So ocean state is changing. Ocean is getting warmer. Okay, that is the reason it's changing. Okay, and we need to quantify this melt rate so that we can project this fresh water to the climate model. Okay, for running in future. So this precise understanding of melting is very important. Okay, and you can see here, this is the mass loss. So the Antarctica is losing its mass at different places. So a lot of inhomogeneity there. So mostly this is your western part of the Antarctica, and this is eastern part of the Antarctica. Western part of the Antarctica is losing mass much rapidly compared to the eastern part. Okay, and of course this mass loss is associated with the warming ocean. This is the temperature of the bottom of the ocean, okay, which is filled by the ice shelf. I'll come back to the point when you're saying bottom of the ocean, okay, because there is a lot of bathymetry is important there. Okay, it is not that I'm talking about that bottom of the ocean is 3 kilometers, 4 kilometers. Whereas the ice is holding, it was a very shallow bathymetry, and I'll come back to the point. So you can hear these are the where the shallow bathymetry there, where the temperature is really high. Okay, and that's why they corresponds to high melting. Okay, in this side temperature is still lower than the freezing temperature. So this side you get gaining of ice. Okay, this is losing of the ice. Now, as I told you, we need to quantify it because this quantification is very important so that we can understand how much is we are losing mass and how much is the fresh water is coming to the ocean basin. And why is so difficult? It's really slow, this one. Okay. So why this is so slow? Sorry. Why this is so complex? Because you can see here, where is the? It's very lagging, this one.
Changing the battery.
Mm. Okay, while he's fixing up, so this is the bathymetry, okay, which was where I'm saying hanging of the ice. This is the hanging of the ice shelf, and this is the where is all activities happens. This is we call as the ice cavity. Okay, this is the typical ice shelf, and this there's a couple, 3 or 4 dominant ice shelves are there in Antarctica. So, working now. So this is the typical ice shelf, okay, and this is the word called ocean is come inside the cavity and melt the ice, okay. This is the call is the CDW. CDW is called Antarctic circumpolar current. This, and there is a one branch here, some circumpolar deep water. It gets into the cavity and they interact with the ice. And then when your ice is melts, what you expect? You expect fresh water. Because ice is melts. What is the fresh water does? It like to go up, but now it has a slope. So it will form a plume and hugging the ice and go up. Because of the fresh water, the boundary layer is so tiny. Okay. If you zoom this one, this is run by a numerical simulation. Of course, this is a DNS and it is scaled down model. But technically speaking, this is the very thin boundary layer hugging the ice, and all this exchange of heat and mass transfer occur across this boundary layer. Okay, this is the typical length which is shown in the meter, but again it is the DNS. But in actual scenario, this boundary layer is order of meter. Okay, maximum 5 meter. So it is a big challenge even for the any model to resolve that boundary layer and understand the melt rate. Okay. Now, the connection. This is your large scale overturning circulation, and I am zooming this part. After this melt occurs, you see this is releasing this fresh water. This fresh water, or sometimes happen, there's a water mass transformation happen. Okay, sometimes you create lot of dense water right here. Because here you also get freezing of the ice. Okay, so melting is occur fresh water and freezing of the ice is called salty water. So with this all combination, you form a different water mass, and this water mass moves out now. Okay, and that will be the part of the our overturning circulation. Okay, so how much is the melting and what is the water mass is coming from the melting? They're very crucial to dictate again the overturning circulation. So it is a feedback loop. And this is again is a zooming view of basal melting from climate change scenario. But you see all this is a typical this ice shelves. One is this one, another is this, another this. There are the 3 dominant ice shelves in the Antarctica, and around this you have ice shelf, but they doesn't have a cavity. Okay, so cavities are very important area where you form this dense water we call as a Antarctic bottom water. Okay, and that part of our overturning circulations. Now, what is the problem? Yes, problem is the modeling. Okay, that's why we want to understand this small scale feature much more accurately, so that we can correct the model. So here is the present state of the modeling. Okay, this is not I'm talking about the global model. This is absolutely regional model, and different model give you a very different scenario of melt rate. Okay, and different pattern of the melt rate. Okay, all these models are only focusing one particular ice shelf. Okay, it's not talking about whole Antarctica. It is very high resolution, but these are the all regional ocean models, and you see there's a huge disparity of the model. And now we come to the point, where is the disparity on what we can correct it? Okay, so is back again, understanding this boundary layer, understanding this heat flux, understanding the mass flux is very important. Okay, rather than using just a simple what is called functional relation. We need to understand that functional relation. Yesterday we talked about this functional relation, right? So we'll come to this functional relation and we'll talk about more about the functional relation. So think about this is a slab of ice. Okay, for a simplicity, I am making this ice is horizontal. Okay, of course in real scenario it is not vertical, not horizontal, it is somewhere there because it has a different angle. Okay, so you can also think about the flow under the sea ice also. Okay, if you are very comfortable. Okay, now there is a background flow. Okay, this is our background flow, and background flow can be highly energetic, can be very weak. Okay, so this is one of the energetic background flow. How many people know us about log layer here? Only one person. Okay, that's good. So in an engineering problem, okay, when there is a very high flow over a bottom layer, you start to getting a asymptotic limit. Okay, so flow get a self-similar pattern. Okay, so in that self-similar pattern, you get these three different layers. One is called viscous layer. Right at the boundary is a viscous layer because you have a boundary. Flow has to be zero. So boundary from you get the viscous stress. Okay, and then you get log layer somewhere here. You see the viscous layer is very tiny. Okay, and then you get the log layer, and then outer layer, and then is a free stream velocity. Okay, there's a different layer, but when you have very energetic stage, this profile is matches with the other system also. Okay, so it is called a self-similar system. Okay, when the flow is not energetic, back again laminar flow. How many people knows laminar flow? Good. Okay, so now you give that to the laminar flow. Okay, in laminar flow we have a analytical solution. What is analytical solution for a laminar flow? What does it looks like? Which function usually we use for laminar flow? Exponential, parabola, hyperbola, parabola. Exactly, you get a parabola, right? And in the parabola, when you take a log axis, it will not give you a straight line. So that means it doesn't have any logarithmic portion. Okay, so that is the where we call as a energetic and non-energetic stage. Okay, laminar flow is a non-energetic stage. Okay, now this is them projecting that boundary layer, correct? But it is not the simple mixed layer problem, right? Here the flow also has two scalar here. Yesterday I talked about these two scalars, right? So now two scalars are there. In addition of there is a background flow. Okay, so if ice melts, what do you expect? What will happen for one scalar, another scalar? Okay, first about the temperature. What is temperature next to the ice compared to the free stream? Temperature means if is the temperature, say for free stream temperature is say for 2-degree temperature, okay, and next to the ice temperature, it is a lower than the free stream or higher than the free stream? Lower, right? That means it will close to the freezing point, right? What about the fresh? What is the salinity compared to the far field? Lower, right? So what do you expect this system? Fresh, salty, fresh cold and salty warm, right? Correct? Yesterday, what is we expecting that scenario? Exactly. So it can be possible. There's a diffusion convection. Okay, and also why is the diffusion convection? Because again this ratio is a huge, again 100 times more. Okay, so you expect this scenario, or maybe the salt is absolutely dominating, you get no instability, you get just a strong stratification. Correct? So you see, one case you expect double diffusive convection. Okay, another case you expect absolutely stratified scenario, or another case you expect these two scalars are not important. Correct? You have only background flow will flowing, right? Is becoming like energetic state. Okay, scalars are no more important, so we call as a What do you call when the energetic flow is control the heat transfer? Anyone? Have you heard about forced convection? How many people heard about forced convection? One. Good. Okay. So how many heard about natural convection? Okay. So natural convection, that's good. So I'll take very less time in natural. Natural convection means there is a no background flow. Okay. And convection takes place. Convection means either is you are driving salt or driving cold water, right? This is a convection, right? Now, in our, it's called a natural, but in a natural system, usually have always a background flow. Okay. So when you have a background flow, then this convection is modified, okay, by the background flow. Okay, that is called force. We are putting a force to the convection. So it's called force convection. Okay. So in the under the force convection system, the natural convection behavior or natural convection scaling is non-practical. Okay. So you see that in under the ice, you have this different regime can be possible. It can be absolutely force system, absolutely natural convection system, or absolutely a stratified system. It's a very interesting. So this is not only ice. It is actually, if you look back, any physical system, it is having like this three combination. Okay. And ice is one of the area you can study very well. Now, this is the, I'm looking at the interface between ice and ocean interface. Okay. And these are all the heat budget. What is meaning of heat budget? Ice is, core of the ice is very cold, correct? Ice core temperature is -20 or -30, right? At the interface, it is a close to the freezing point temperature. That's why you are melting, right? So it is not the core temperature. So there is a conduction of heat from the core. It is a conduction of heat from the interface to the core, right? And there is also heat coming from the ocean, right? So that was represented as QT, and this is the QT ice, and this is QT ocean, you can call. Now, because of this imbalance of the heat, either ice will melt or ice will freeze. Okay. If his ice core is dictate, then you grow ice. Okay. If his ocean will dictate, then you melt the ice. Okay. So that's the combination. Now, the similar thing is also happen for a salt, right? Ocean is technically salty. Okay. This is very interesting. So even ocean is sitting at 0° temperature next to the ice. Ice has to melt because ocean is salty. Just like you spread the, what is called, salt over any ice, it will melt because it depresses the freezing point. Okay. So there was a debate in Antarctica, like, is it Antarctica is just melting because of it's just dissolving? It's called as a dissolving, or it is a melting. There is a loose term between melting and dissolving. Some people say Antarctica is just a dissolving because ocean is salty. Ocean don't have to be raised temperature more than 0°. Even is not even more than 0°. Even ocean can stay at -1°. Ice has to melt because ocean is salty. Okay. So this is a very interesting point. Because of the salinity, ocean ice can melt. Okay. Which was one of the biggest drawback in the present climate model. Okay. Because, or even in this other models we have it because we don't need to take into account of salinity. Okay. Because the scales of the salinity so small, we actually don't have the capacity of resolving the salinity boundary layer. So Antarctica was actually impacted by more salinity than your temperature boundary layer. And salinity budget, of course, you never find salt in the ice. Same is the rainwater, right? We never have a salt in the rainwater, correct? That's the reason from interface to the ice, we can think about there is no salt transport, correct? Very negligible. But there is a salt transfer happen between the ocean and the interface. So salt molecule get diffused at the interface and drops its melt rate and melting is happening. Now, how many people have seen this equation? Not in the context of oceanography, not the context of Antarctica, context of anything. You see, heat flux is proportional to the delta T and velocity. This is called bulk formula of heat flux. Okay, this is the very common, like that is the way the heat transfer occur between atmosphere and ocean. Okay, and this is nothing but heat transfer between ice and ocean. Okay, this is called bulk formula. When you say bulk formula means we make this formula so simplified so we can plug velocity and temperature difference, we get a heat flux. Of course, the problem is that we need to have a constant there. Okay, that constant is playing an important role of the total melt rate or total heat flux. Okay, now this is we call as a frictional velocity. How many people know frictional velocity? One. Good. So frictional velocity. Okay, what is the frictional velocity means? So say for there is a flow over a flat plate, right? When you say flow, you see it is not just a single velocity, correct? The velocity is high away from the boundary, we call it a free stream, right? As you go closer to the bottom of the surface, it is a zero velocity, correct? So when you say velocity, what is the velocity? There's so many velocity. Which velocity we should report? We can only report the free stream. Another velocity we report is called internal velocity, or based on the frictional force. That was based on the friction associated between the flow and the wall. Okay, so it's called U star. Okay, and that was based on the drag force. Okay, wall stress. There is always a wall is giving a stress. Okay, so from where we can calculate the frictional velocity. But the problem is that to calculate that stress, you have to go and measure it in Antarctica, right? We don't have a capacity, right? Measuring the velocity profile all the way. Even experiment is difficult to measure the flow next to the bottom surface. Only can DNS you can able to capture. Even the large scale model you cannot, because nobody knows what is exactly the next grid point where the velocity is changes with the exponentially or parabolically or whatever, right? Until unless you know these points, you cannot fit the line, and from that line you calculate a gradient, and from that gradient you calculate U star. So it is very difficult job. Okay, so to simplify that job, what we do? We say this frictional velocity is proportional to the background flow, because everybody measure background flow, right? In atmosphere, in ocean, you can just measure it away from the boundary, right? 5 kilometer or 10 meter height or ocean is much easy, you can measure it. So if come on, if we have a relationship of these two, we plug it here, then you see everything is depends on the external parameter. When you call external, that means very easy to measure before you running any simulations, right? It's called external parameter. U is external because you know free stream. Delta T is the external parameter also. You know is free stream temperature, and you expect the temperature should be ice is around 0. So roughly speaking, 0 or -2, you don't make that mistake. So it's 0, say for. Until unless there is a 0 and minus 1.9 or 1.2 because of the depression of the freezing point. Okay, so it's a very interesting. So there is this delta T choosing is very crucial, and also the functional relation. You know what is the functional relation? This one, what is the coefficient here? You usually put it. How many people knows this function relation and then coefficient? No one? Drag coefficient, how many people are aware of drag coefficient? Exactly, that relation is give you drag coefficient. Okay, but is it drag coefficient universal? How many people agree that drag coefficient is universal? Is just a one number? Raise your hand. How many people is agrees that drag coefficient is not universal? Is function of time and space? Exactly. Look at it is intuition says. Okay, but we don't have a capacity. We plug this same drag coefficient and run all the models. And then you got a mismatch. Of course, we are making a mistake in here. So of course, you're getting different result. Okay. Same is this coefficient is here. This is called transfer coefficient. Okay. And the same thing, we plug this number and then we get a mismatch. We're saying, oh, there is something is different. Of course, these numbers cannot be universal. So these numbers are also very much changes for a different flow condition. And that's the very important thing to know. Which flow regime I am, which values I should plug in. Now, this is a very interesting point we came across, is this drag coefficient and this transfer coefficient, those values are very old. Very old means this has been done in 1960 or 1970, even not flow, the condition we have right now Antarctica. We're running over a simple flat plate. Okay, flat plate simulation over a flow, and then you got the drag coefficient, and that has been used till now for all the models, anything you see. So there is a need to change, or there is a need to understand why this drag coefficient we should use it. Okay, and is it there realistic? Because that scenario even doesn't have a natural convection. So once you have a natural convection, what is the point of even drag coefficient? Because now the flow is created by naturally, correct? It doesn't have an imposed velocity. So we don't know this functional relation is right. So this is like, another extreme limit when there is a no energetic flow, or flow is laminar or zero flow. You see, we cannot use any of this relation. So that was the condition called natural convection. Okay. So in the natural convection, we also try to calculate the drag coefficient, but that has no meaning. Okay, the transfer coefficient has no meaning because the functional relation doesn't exist, because functional relation is not depends on the U, it depends on the temperature difference or salinity difference across the boundary layer. Now, this is I already talked about. So similar for a salt, also they use the same functional relation, okay, called salt transport, heat transport and salt transport. These are called again bulk formula. Now, here is the things. So now we understand there is a different scenario exists. Okay, can we test it? Okay, because this never been tested. Always we are just using the same, old equation and trying to get every result from this one equation. It is not possible, right? So it's same like you want to paint and you want to, what is called a nail. Okay, you have only hammer. You can't paint with hammer. You need brush for the paint and hammer for the nailing. So we need to understand where is the brush is required, where is the hammer is required. Okay, cannot unnecessarily using the same hammer for a painting. Now, that is the reason we have such a disparity of our understanding. Okay, of the heat flux and salt flux, and end of the day is a melting. Now, how to address it? Of course, it's very difficult to address from the large model. We have to learn from the small scale model. And just to look at this, based on that equation and based on the observed melt rate and different area of Antarctica. This is the observed, and that is the model, based on this functional relation, the old functional relation. Look at the mismatch. Is all over the places. It can be order 1 higher, it can be lower. So some places they're working well, some places they overestimate, underestimate. So we found underestimated by 10 times or overestimated by even 10 times. So it's like all over the place. Okay, so that we motivates to revisit this scaling and revisit this problem in large eddy simulation. Okay, so it's a very simple way. We make a box and we using the periodicity in the horizontal direction, and we put a ice there. Okay, so one simplification here, this ice don't deform, it remains as a slab. Okay, that was the one condition. Okay, of course we have to do a lot of assumption here, but try to make as simple possible so that we can understand the fundamental. Okay, that's the objective. And here we also have a geostrophic flow, like rotating boundary layer. So we give a geostrophic flow underneath. Okay, that geostrophic flow we can control by a pressure gradient, because geostrophic flow pressure gradient. So we can control geostrophic. We can make an energetic geostrophic flow and non-energetic geostrophic flow. Correct? And then these are the one of the important parameter there. Okay, which decide the grid spacing. Okay, one is the called viscous scale, which is defined by the again that frictional velocity, because viscous frictional velocity they're next to each other. They're called internal scale. Okay, and then this is another called planetary scale. Okay, where the rotation is important. So you have to resolve this scale so that we can get the better estimation of the viscous stresses. Okay, even this is LES, still is very highly resolved LES. Okay, so our vertical resolution is the same as a direct numerical simulation. So it's a very expensive simulation to run. Now, also there is another interesting parameter here, is called stratification. So we come, this type of length scale we got from the atmosphere. Atmosphere people use a lot Overkov length scale, whereas the stratification matters. Okay, so this was the B is here, is the buoyancy flux. Okay, and the U star here is the frictional velocity. So that means there's a two types of forcing is involved. Yesterday I talked about these two forcing, correct? Buoyancy forcing and mechanical forcing. So U star is represent the mechanical forcing and B is the represent the buoyancy forcing. So they are now looking at the who is the winner. So that is the way we can decide another length scale. Okay, that's called Overkov length scale. Now let me not playing. Something happened with all my movies, nothing is playing. Okay, so no time for movies, so let's come to the science. Okay, so now we look at the regime. This is my energetic plane and this is my T star means is the thermal forcing, correct? So, and this thermal forcing is also embedded the salinity forcing. When you say embedded means this thermal forcing is the background temperature minus the highest possible melting temperature based on the background salinity. Okay, so freezing point at that background salinity. Okay, so that means if I have a zero salinity, this value will be smaller. Okay, because my interface is now at not zero, my interface at now -2 at 35 PSU. Okay, so that will expand this regime. And now this one. So we're going to conduct couple of simulation around this space to understand which space we expect these three different scenario. Now, this is called low thermal driving. This is the way thermal driving is increasing. So low thermal driving and energetic flow. Okay. We expect the simple boundary layer. Okay. Just like a flat plate boundary layer. And here, what is I'm showing here is just like an ocean mooring. I'm taking one line from my domain and looking at its temporal evolution. Of course, initially, I don't have a boundary layer, right? So that's time I have, the boundary layer has to grow. After it will grow, it will get a quasi-steady state, okay? And this is my quasi-steady state is. What is showing is here, I'm showing the turbulence kinetic energy, that boundary is turbulent or not. How many people are familiar with the turbulent kinetic? How you define turbulence? Can you raise your hand? Turbulence kinetic energy. What is kinetic energy, by the way? How many people knows kinetic energy? Good. How many people know? Now in the kinetic energy you have a U, right? Now instead of U, you write as a U prime. So it is turbulent kinetic energy. Correct? Happy? Okay. So that means is the deviation from a background state, and the deviation can be done in the temporal average or spatial average. Doesn't matter how you define it. Okay. So U prime replaced with U is the turbulence kinetic energy. Now, temperature. As I told you, this is my background temperature, right? As you go here, it is become cold. But look at the background temperature. It is already minus 0.22 degree temperature, right? So it is already very cold. It is a sub-zero temperature. And still is Antarctica is melting because of the salt transport. Okay. And n square. You build a mixed layer and underneath you build a thermocline. Okay. That is similar like, interface is what is called upper ocean. You have a mixed layer and you form a thermocline. The similar things also found in under the ice. You have a mixed layer and form. As soon as you have formed a mixed layer, you get a thermocline. Now, increase the thermal driving, keeping the velocity forcing same. What I'm going to expect? More melting or less melting? Increase the thermal driving. More melting, correct? Happy, everybody agrees, right? Nobody saying less melting, correct? High melting. High melting is also at the cost of high fresh water, right? Because you melt water. So now it is a very counterintuitive. Oh, I have a lot of mixing, lot of turbulence there, but now I have a fresh water there. So what will happen? Fresh water is going to dictate the turbulence now. It will build a stratification. Okay, so exactly that is happening. At high temperature, you build a strong stratification. You see here? You build a strong stratification. And now this all the mixed layer is start to collapsing. Okay. So even high melting, you start to collapse. Velocity is constant. You see, velocity is not playing any more role. It is now controlled by another scalar, which is your fresh water. Okay. Hope this will have, I'll play this movie. No luck with any movie. Okay.
Don't do the slideshow.
Okay. No, nothing. It's just like the interface. I don't know. It was working fine. Anyway, that's fine. It's not interesting. Okay, let's get back to the real science. Okay, this is actually happened. If you have a low thermal driving and high thermal driving, you get a very different boundary layer structure. Now, we identify at the high thermal driving, we going to a regime called stratification is dominating. Okay, so from this one is called well mixed layer. Well mixed layer is a highly energetic flow, which is controlling the heat flux. So that means we might expect the scaling which is proposed in 1960, 1970, and still people are using it, is working. So we feel like, oh, there is something was there. Okay, so it's good. At least it's working. But once we go to the high thermal driving, things have changed completely. Okay, it is become a stratification is important. Now, we haven't expected this regime where flow is non-energetic or flow is zero. We'll come back to the point. Now, let's test some scaling. When well mixed regime, we have an existing scaling. In a well mixed regime, the background stratification is important, not the stratification is built by the fresh water, correct? Because built by the fresh water is an internal property. Background stratification, because still is a stratification is there because ocean is stratified. Okay. Now, rotation is also important. U-star is also important, right? So U-star is important, rotation is important, background stratification important. That means if you want to get a scaling, it has to be combination of these three, right? That's called the combination. Okay, it's no magic. It's the combination of the three. You can try many ways. Only you get this form to get a length scale. There's no other way you can get a different form. This is the way you get the form. Okay, now we test. It is operating for those boundary layer thickness, we got it for all this regime called well mixed regime. Yes, they're collapsing so nicely. So if I plug this one, you get this scaling and the data are collapsed. So that means that scaling is operating. Okay. So boundary layer, we can expect this boundary layer should be scaled by that. Now, another scenario. Okay. When the stratification is important, I mentioned about the Overkopf scale, correct? This was is here. You see that? So that means now background stratification is irrelevant. Now this new stratification which is evolving from freshwater is important, correct? So now we have again U star, F and B, right? Do all the permutation combination, you come up with only this scaling, okay? And let's try the scaling. We see the scalings, but the other points are not matching. And we got a stratification condition, okay, where the stratification is important based on this sigma, or not sigma, but it's called mu. What is this called? What is the sign called? Mu, yes, mu. So the mu is called stability parameter. So stability parameter is more than 1, the stratification is very important. Less than 1, we can still use our well mixed regime scaling. Now, another interesting point is called, there is a flow is so less energetic. So U star is no more important in the problem. What do you expect now? Exactly, natural convection. All sorts of convection is possible now. Okay. So in here, only one possibility is there, is the double diffusion convection, because it's a fresh water. Okay. When it's a freezing of the ice, then it's a full convection, because you reject the salt, ice is also cold. Okay. But here is a double diffusion. So double diffusion is very important. For me, I feel like Antarctica is all about double diffusion. Okay. When you first time we wrote this paper, we read this, that what is called Antarctica ice is driven by the double diffusion. Many people disagree. But now people actually go and measure it. They find like everywhere they founding double diffusion in the another Antarctica. But this is going to be happen because you see there is a cavity there, right? In that cavity, how can you drive a energetic flow? It is impossible to drive an energetic flow inside this small cavity. Okay, so that flow is very less energetic. So there is no way you can choose a velocity which is 100 or 300 meter distance and just predict that energetic flow is creating a U star. It is impossible. Okay, so it has a less energetic system. It is going to have a convective driven system, and if it's a convection, it is a double diffusion. And we see it, if you run this system in a very less energetic form, we see the formation of the layering. Okay. And I don't have to explain this one. I told you yesterday, right? Why is double diffusion? Now, you see this energy equation, right? Now is this TKE. Somebody has to create the TKE. Somebody has to destroy the TKE, right? Dissipation is destroy the TKE and somebody has to create the TKE. Okay. So depending who is creating the TKE, okay, if is the buoyancy forcing is creating the TKE, we call as a buoyancy flux. So if the buoyancy flux is plus, that means the TKE is created by, turbulence is created by buoyancy, correct? If it's negative, that means buoyancy is not creating the turbulence. Somebody else is creating the turbulence. It's called shear production. So background flow is creating the turbulence. Okay. So this what is called shear production and buoyancy flux is a very interesting term to understand who is creating the turbulence in the first place. Okay. So if the turbulence is created by first place is by convection, then buoyancy is plus. You see, you get a plus quantity under the boundary layer. You get minus quantity under the boundary layer when there is a shear dominated. Okay. So you can immediately see that, okay, if my buoyancy is dominated, that means no way I can use my previous scaling. Doesn't matter how many people are using it. It is not going to operate. Now, we should expect a different scaling here because it doesn't have a U star dependency. You have B, buoyancy flux, and background stratification, because now the background stratification or the background forcing, we have to be worked against the existing ambient stratification to driving a mixed layer. Correct? Because if there is a stratification there, otherwise mixed layer is continuously grow infinity. Correct? There's somebody is holding the mixed layer, and that was by background stratification of the ocean. Okay, so background stratification is important, and this forcing is important from the top surface, which is here for this particular scenario, not the salt. It is the cooling, because you're cooling the top surface. Your stratifying system is a stratified system, and you're cooling from the top surface, and you get this scaling. Happy? Now we have this three family. We actually got it, and let's see how we can plug it back to the Antarctica. Again, we go back and put it all the values. We found it now is whatever the area we expect, the melt rate we can able to predict it. Okay, this is my oil mix regime, where is the existing bulk formula people are using it. Okay, that is also there, but only few area of Antarctica. Okay, so this is the way we can remove the underestimation and overestimation. Okay, that's it from this one. I think, okay, let me see how fast I can move the, another movie is not working, this is I'm not go. Okay, now this role of the small scale. You see this scenario, right? Yesterday I talked about the Rayleigh-Bénard convections, right? But ocean is not a Rayleigh-Bénard convection. Ocean is much more interesting, not like atmosphere. Okay, atmosphere is scenario is a Rayleigh-Bénard, because you are cooling from the top of the atmosphere and heating from the bottom of the atmosphere. Ocean is not like that. Ocean is like this. Okay, so this has always a debate. This can drives turbulence or can drive a overturning circulation. Even it doesn't have any net heat transfer in an integrated sense. When you say integrated, means horizontally integrated sense, it doesn't have any heat transfer, correct? This is zero. Rayleigh-Bénard case, there is a heat transfer at every level. Okay, same as the atmosphere is every level there's a heat transfer. Ocean in an integrated sense is not. When you say integrated, that means locally there is a heat transfer, but not horizontally integrated sense. How many people feel like this have, how many people believe that this cannot have a turbulence? So everybody believes it has a turbulence. Okay, so there's no need for going another couple of slides. Okay, then I move fast. Okay, I'll take another extra 5 minutes. That's fine. Okay, so this is the scenario called, how many people knows about available potential energy here? How many people knows potential energy? Same. So potential energy and available potential is how much is the potential energy available? Not the all potential energy is available to do work, right? Correct? So this is the scenario. You see one case is, this is the, here I'm making a dense water, and I have also here I make the fresh water, the same amount of exchange, delta rho. Make it delta rho is bigger here and delta rho is smaller here, and rest of the domain I make it the same rho. In this case, everything is the same rho. Correct? You see this case doesn't do any motion, and this case is driving the motion. Both system has same potential energy, but one system has more available potential energy. That's the first thing is called available potential energy. I'm not going to the definition. The same is there. Both system has same potential energy, right? So which one thing is have a more available potential energy here? Which one is fall? Correct? So that means this has higher available potential energy. So potential energy is not the right way to measure it. The system is the available potential is the right way to measure is how much is available for doing work. So same in movie. So I put this heating and cooling. You get here. This is the showing of a temperature. You see here. It is not a Rayleigh-Bénard scenario. It is a very interesting scenario. It is like a half Rayleigh-Bénard. Okay. Why say half? You get small scales because you're cooling here, right? You get small scales here, but at the same time, you create a pressure gradient, large pressure gradient. That means you are drawing a big volume of water from one side to another side. Okay. So this was the kind of scenario of our equator and pole. So this side is your pole and this side your equator. And cooling means technically speaking, you're cooling from atmosphere and this is heating. Okay. So cooling, you create small scales and at the same time you create large scale. So this type of convection, of course, I didn't give the nomenclature. This type of convection we call horizontal convections. Okay. It has the capacity of drive small scales and large scale together. This is the first time it's driving both scale at a together. So it can drive a planetary scale and down to the Kolmogorov scale. These are the Kolmogorov scale. And at the end, you get this end wall plume. Correct. Of course, because of the small scale, you really need to resolve it. If you don't resolve it, you don't get it. So technically speaking, this scenario cannot be run in a hydrostatic model. It has to be run in the non-hydrostatic. But the challenge is how? Because we are missing. So this is the reason we decided to do this problem in more like, idealized fashion. So this is called as a dynamical similarity fashion. We able to capture the big planetary scale and small turbulence scale. So you're resolving. What is you doing it here? We make it smaller and the same dynamical regime. Oh, good. This movie is running. You see here, you see small scales and they're migrating. Okay. This is very scenario you can think about in atmosphere Hadley cell. Now, I crank the Rayleigh number because there's a challenge. Okay, what is going to get? We get more and more turbulence activity in there. Now, this is the like a scaling back again. Scalings are very important. Okay, so if the system is driven by one single scalar, we have only two equations, right? Momentum equation and scalar equation, and we're looking for a steady state solution. So momentum equation, we can think about two-dimensional fashion. So we can create a stream function equation, correct? In the stream function equation, there's always a three terms. One is the inertia terms, another is the buoyancy term, another is the viscous terms, right? When we are very low energetic stage, the inertia term is not important. It has the buoyancy and viscous term, and your heat equation is the two terms, okay? Two equation, two unknown. You get the scaling relation. Happy? Now, when the inertia is important, like a very energetic state, viscous is not important, right? So you get a different balance and you get this regime. Very interestingly, the product between Rayleigh number and Prandtl number, there is a no nu. The viscosity is not important. This is we call in the regime of infinity Reynolds number, correct? Viscous force is not important, but the kappa remains important because this is the way we are getting energy from the atmosphere to the ocean. Now, we got the scaling, we tested the scaling against the, what is called, experiment. We got nice balance and we move on. And we are looking at the different regime. That's fine. Now let's move on. So now you understand the very basic, okay? It is still not ocean because it doesn't have, what is not there in here? Another big component is not there here in this all simulation. Salinity, what else? Even important than salinity. What is not here? No. Another. What is not here? Rotation. Is rotation is there? No, right? So rotation is not there. Now we plug the rotation. So we put the same domain, we put a rotation. Okay. Once this rotation is important, the flow is, horizontal flows are very important, right? Because now flow cannot go north to south, it has to rotate. Okay, so now with the rotation, this flow is behaving as a geostrophic and buoyancy balance. Okay, and very interestingly, oh come on. At the middle of the domain, you follow a strong geostrophic balance, thermal wind balance. So the flow has to cross from east to west. Okay, this is the scenario was very, very common in ocean. There is the Gulf Stream, Kuroshia currents, right? Southern Ocean. All these things are, there is a geostrophic flow. Now, I have a solid boundary both sides. So if it's a solid boundary both sides, it cannot, it hits the boundary and then again go to the north. So it will now form boundary currents along with the geostrophy. Okay. And this is the increasing my rotation. You see, without rotation, I have only end wall plume, right? Because there is a fresh water, not there is a what is called stratified water is coming underneath and blocking the convection. But when you have a rotation, that water is now follow as a boundary current and move from east to west. So there is a no blocking mechanism. So the entire water column will sink in our southern end. Okay, so you get open ocean convection. So this is scenario is very similar to your North Atlantic open ocean convection. I'll quickly go the scaling and then I finish it. Now, when the rotation is important, inertia is not important, correct? Viscous force is already not important. You have geostrophic balance and then your thermal equation is the two term is always important. Again, two equation, two unknown. We get this interesting scaling by Rayleigh number and Ekman number because now is Ekman number is important. And we tested this scaling with the experiment and numerical simulation. We're quite happy with the scaling. And now we draw a regime diagram of the ocean. This is the first effort of regime diagram of the ocean. Where is the ocean is lying? This is the axis of rotation. This is the axis of buoyancy forcing. Of course, we don't have a wind here, but that was another day. I will talk about that story. But in the non-wind system, when you increase the rotation or increase the buoyancy forcing, you first is the no convection, right? And now we get a convection. So you get all convection here, and now increase the rotation, you start to moving in the geostrophic regime. So this wedge is the geostrophic regime, and this is your inertia dominated regime. And more rotation, what will happen? All inertia force, all the forces values. So you get a conduction regime. Okay, this is also happen in the mantle system. So we believe the ocean is lying in border because geostrophy is not the only one is driving the ocean. It has also inertia force. So it is oscillating between this boundary of geostrophy and inertia because we see the geostrophic breaks down. Okay, and this breaks down because of this again small scale convection. Okay, this is my last movie. So here we force this system. Now is another level of complexity. We use beta plane instead of along with the rotation. We close the domain. What we see here, you see this is a boundary current, and then boundary current is moving the east to west to east, and then the whole boundary current is sinking. Okay, so this was one of the simplified system of North Atlantic scenario. This is your Gulf Stream, western boundary current, Gulf Stream, and eastern boundary current, and open ocean convection without having any wind forcing. We tested also wind and we look at the scaling. Can I have 2 minutes more? Okay. Now, I don't have a boundary now. Okay, side boundaries I am removed. What will I expect if I remove the side boundaries? Flow will just move from east to west, right? What you'll get is Southern Ocean. So Gulf Stream becomes Southern Ocean. Exactly is saying is there. No rotation in a open boundary into the page and out of the page, you get overturning circulation. You remove the boundary, you see bunch of eddies, but there is a zonal current that's supported by geostrophy. Okay, so we tested this one in our simulation. And we exactly got this Southern Ocean scenario, and we also put wind because Southern Ocean is a wind, and we like to see that is the wind has any effect of this transport, any effect of this overturning cell. I didn't find it. Okay, so that is the biggest posing a concern when you are resolving this convection. Do you wind play a big role in the driving this system? Okay, so it is a challenge for the model. When we are resolving this one, then we might understand this buoyancy forcing is much better, but not now at the present state, where the normalization of the buoyancy forcing is poorly done, or the normalization of the small scales are poorly done. Okay, I stop here. Thanks.
So we are running short of time. We can take 2 questions, maybe. Yeah.
Thank you for the talk. So can you elaborate on the modification?
It's a little bit louder. I can't.
So
hear.
can you elaborate on the modifications you do for applying boundary condition on ice? Like,
what is the modification?
In the boundary condition when you are applying it on ice, like what is the boundary condition?
Oh, what is the boundary condition?
On
Okay.
ice?
We put 2 boundary condition, 3 boundary condition in the ice, or not 3, it's a 4 boundary condition. First, we'll talk about the velocity boundary. Velocity is you can put slip condition and no slip condition, right? Depending on the how rough you want to make ice. So it's depending. If ice is very rough, you can put some roughness boundary condition for the momentum equations, right? Of course, no penetration condition. There is nothing is penetrated in the ice also. Okay, the velocity. But for temperature, depend on the temperature or salinity. If you have a force by temperature and salinity, there is a 3 boundary condition. One is the flux boundary condition for temperature flux, for salinity, salinity flux, and in the top of that, they coupled by the freezing point depression equation. How many people knows freezing point depression? Right? Is the freezing point depression. So in that particular salinity, what will be the melting temperature? Freezing point depression equation also function of pressure. So you can also include the pressure there. But for now, we are not including the pressure. That's it.
So, well, I see no questions then.